Hi everyone! So in this video, we're going to go ahead and discuss different calculations related to acids and bases. So let's go ahead and get started. Okay, so one thing I do want to touch base on before we jump into those calculations is how chemists represent concentration of different compounds. And you're going to see this a lot this unit. So in a way to abbreviate our writing, what we use is square brackets around whatever compound we're talking about to distinguish that we're discussing its concentration, or also known as the molarity, the amount of stuff dissolved per liter of solvent. So in the case of hydronium ions, commonly talked about for acids, we want to find the concentration of them. So we would put H3O plus 1 in square brackets to represent the fact that we want to find the concentration of the hydronium ion. Or another one that will be common for this unit is the concentration of hydroxide ions. So we put OH minus 1 in those square brackets. That means that we're trying to find the concentration of the hydroxide. So this all relates back to the idea of that pH scale. And we've talked a little bit about pH before, in that it goes from 0 up to 14. 7 smack dab in the middle is neutral. Anything less than 7 is going to be acidic, and 7 up to 14 is the basic region. Well, pH is actually a French phrase which stands for the potential of hydrogen, talking about how much hydrogen ions do we have in our solution. And the pH scale is a negative logarithmic scale that measures the concentration of the hydronium ion, which is hydrogen ions bonded to water. So negative logarithm, meaning we're going the opposite way, we're not increasing, we're going to decrease. And logarithm, meaning we count by units of 10. So if we look at this, a neutral solution of water has a hydronium ion concentration of 1 times 10 to the negative 7th. That corresponds to a pH of 7. Now, if I had a slightly acidic solution, 1 times 10 to the negative 6th, meaning I have 10 times the amount of hydrogen ions, then my pH would be 6. So in the case where we have 1 times 10 raised to some number, the number that we are raising that compound to corresponds to the pH. Okay, so if we have a 1 times 10 to the negative 12th, then we have a pH of 12. If we have a hydrogen ion concentration of 1 times 10 to the negative 2, then it's a pH value of 2. So as I said earlier, pH is a negative logarithm. So if I go ahead and actually write this out as an equation, we get pH is equal to negative log of the hydronium ion concentration. So let's go ahead and actually see how to put this into our calculator to get an answer. Okay, so let's go ahead and try this out. A neutral solution has a hydronium ion concentration of 1 times 10 to the negative 7th. What is the pH of the solution? Well, I have my equation that pH is equal to the negative log of the hydronium ion concentration. So I'm going to take that value in scientific notation and just plug it in for my square brackets. So I know that the pH is equal to the negative log of 1 times 10 to the negative 7th. So the next step here is to put this into our calculator. So one really important thing, this can work for both graphing calculators and scientific calculators. Just make sure you have that log button. Keystrokes might be a little bit different for putting this in your calculator, but I'm going to show how to use it using a graphing calculator similar to mine. So you want to first find the negative button, which on my graphing calculator is way at the bottom in parentheses. So I'm going to press the negative button, and then I want to press my log button. And then from here, I just need to type that scientific notation number. So 1 second EE negative 7, and then close the parentheses. Hit enter, and that gives us our value. So our pH for this solution is 7. Okay, so that isn't too bad, but sometimes we're asked to do the reverse. So we want to find the hydronium ion concentration when we're given a pH. For example, determine the hydronium ion concentration of an aqueous solution that has a pH of 4.0. Well, if we take our equation, we substitute 4.0 in for the pH, we get this really negative, really yucky negative log is equal to the hydronium ion concentration. And this leaves us to wonder, where do we go from here? Well, for those of you who really love math, you're probably like, no problem, this is easy peasy. But for the rest of us, you're probably scratching your head. So let's go through and actually show you the steps involved. So we're going to rearrange the pH equation to go ahead and actually solve for the hydronium ion concentration. So the first thing I want to do is I want to take the negative of both sides. So we get negative pH is equal to positive log of the hydronium ion concentration. And now I want to get rid of that log. So there's actually something in math called the anti-log, which is basically 10 raised to whatever you're discussing. So if we go ahead and do that, we end up with a much friendlier equation, which is 10 raised to the negative pH is equal to the hydronium ion concentration. So that would be a much nicer thing to use. So if we have that example problem, we're going to take that 4.0, substitute it in for the negative pH. So we get 10 to the negative 4. If we go ahead to solve for that, we get 1 times 10 to the negative 4 is the hydronium ion concentration for the solution. So let's go ahead and try this out with a different example problem. Okay, so for this next question, we are asked to determine the hydronium ion concentration of an aqueous solution that has a pH of 2.5. So we're going to take that rearranged pH equation. So the hydronium ion concentration is equal to 10 raised to the negative pH. In this case, we're plugging in the value 2.5 for that pH. Don't forget to keep that negative sign. That is important. Now, when it comes time to plug this into our calculators, there's 2 different ways you can do this to get the correct answer. The first way is you type in 10, and then you use that little caret button to have the exponent, and then type in negative 2.5. That gives you the answer. The other way you can do it is if you actually look with the log button, there is the anti-log kind of built in. So the way that we do it is that second log gives us 10 raised to the power. So now we do negative 2.5. And you can see both ways, I get the exact same answer. So for this, we're going to say that the hydronium ion concentration is 0.0032, because I'm going to round in this case, so my sig figs match. I have 2 sig figs here, 2 sig figs here. And then don't forget the unit. So molarity does have, concentration does have a unit of molarity, so I'm going to do a capital M. This is different from pH and pOH where they don't have units. Okay, so we also have something in chemistry called the pOH. So pH is a measure of the hydrogen ion concentration, or hydronium. The pOH is a measure of the hydroxide ion concentration. And it's also a negative logarithm. So pOH is equal to negative log of OH minus 1. So let's go ahead and find the pOH of this solution. Okay, a neutral solution has a hydroxide ion concentration of 1 times 10 to the negative 7th. What is the pOH of this solution? So I know that pOH is equal to a negative log of my hydroxide ion concentration. So I'm just going to go ahead and plug that value in to my equation right there. So pOH is equal to a negative log of 1 times 10 to the negative 7th. So from here, I'm just going to plug this in my calculator, and it's basically exactly the same as what I had before. So I'm going to do negative log, and then I'm going to type in my value that's in scientific notation. So 1 second EE negative 7, close my parentheses, and that gives me a pOH value of 7. And for pOH, just like pH, I do not need a unit for that. So that is my answer. Okay, so just like sometimes we are asked to find the hydronium ion concentration from the pH, we can also be asked to find the hydroxide ion concentration from the pOH. So we're going to go ahead and kind of go through that same derivation as we did before, taking negative of both sides, then taking the anti-log of both sides. So we can find out that the hydroxide ion concentration is equal to 10 raised to the negative pOH, which again is much easier to use when you're finding the hydroxide ion concentration. Now, one other really interesting thing about pH and pOH is that they are related to one another. As the pH, or the amount of hydrogen ions, goes up, the pOH goes down, so that both of those values equal 14. Okay, so it's always true pH plus pOH is equal to 14. Okay, so let's go ahead and try an example. This is actually going to combine some of those different equations together. So let's try this one out. Okay, so let's go ahead and work through this final problem. What is the pH of a 1.0 times 10 to the negative third molar NaOH solution? So this is a little bit different because it's giving me the overall concentration of this whole thing, not just of the particular ion. So I want to think, when I break up sodium hydroxide, what does it break up into? So hopefully you feel confident saying that sodium hydroxide will break up into sodium ions and hydroxide ions. Okay, and it's 1 to 1 because we just have one of each ion, so we're good there. So if I have 1 times 10 to the negative third molar concentration of my sodium hydroxide, since I have a molar ratio of 1 to 1 to 1, I know that these compounds must also have a 1 times 10 to the negative third molar concentration. So that tells me that OH minus 1 is equal to 1 times 10 to the negative third. However, I have OH and I want to find pH. So I can't just plug this in for a one-step problem because I can't use OH to find the pH, not directly. So let's first find the pOH. Okay, so we know the pOH is equal to a negative log of the hydroxide ion concentration. Okay, so if I go ahead, plug that in, negative log of 1 times 10 to the minus third, we find out that pOH, with the help of our handy calculator, negative log of 1 second e negative 3, gives me a pOH value of 3. Okay, so that's helpful information, but not our final answer because we want to find the pH. This is the pOH. But we know that those two values are related. So we know that pH plus pOH is equal to 14. So if I go ahead and substitute in my value for my pOH being 3, I can find out that my pH is equal to 11. Okay, so just to recap this problem, I was given the concentration of my initial compound before it was dissolved, but because I had a 1 to 1 molar ratio, I was able to find the concentration of the hydroxide ions. Now, once I know the concentration of my hydroxide ions, I found my pOH because I couldn't find pH directly. So that gives me a value of 3. And then I can plug that into my relationship of pH plus pOH is equal to 14 to get my final answer that I was asked to find, which is pH is equal to 11. Okay, so I hope this helps. If you have any questions on calculating pH, pOH, any of those ion concentrations, please let me know. I'm here to help. Otherwise, have a great day, everyone, and thanks for watching. Bye.